Today, we are introducing programmable logic controllers, or PLCs. In the first part of the course, we studied combinational logic. And you could think of these types of logic circuits as being represented by some function, where the binary variable y, say, is a function of the three binary input variables a, b, and c. And we learned how to use k-maps to minimize logic functions, how to represent them in terms of logic gates, and so on. Then we moved to sequential logic, and that then takes your combinational logic and adds things like basically D flip-flops and other types of devices that can serve as memory devices. And now we can have something where time is involved in the process. And in particular, we had the kind of the paradigm of a finite state machine. And so this would be a system with various states, and then that machine transitions from one state to another in response to inputs and the current state of the system. When it comes to actual physical implementation, we talked quite a bit about what we could call hard wired circuits. Circuits in which you choose various logic gates and flip-flops and etc., and then you wire them up, maybe solder it on a printed circuit board or something like that. But a drawback of that is that once you've built your circuit, it's fixed, and it's somewhat difficult, or maybe even impossible, to make significant changes. And so we talked about programmable logic. And this could be based on things like fuses being blown to specify the connections between logic gates and so on. And programmable logic might be a one-time programmable type of circuit, like if you're blowing fuses and they're not resettable. Or you could use something like electrically erasable programmable read-only memory to specify the configuration of the circuit, and that could be erased and then rewritten. And so things like field programmable gate arrays would be an example of that. Okay, but there is also programmable logic in terms of software. So this is all hardware here. And what we could call, instead of software, we would call firmware. But it's also possible to have programmable logic which is based on software. Obviously, computers are an example of that. But the type, you could say, type of computer or microcontroller system that we're going to be interested in are so-called programmable logic controllers. Now, these are essentially, certainly these days, microcontrollers embedded in a platform that has input and output modules and possibly other modules like communication, which are appropriate for interfacing with industrial production equipment. The first PLC was developed in 1968 for General Motors and was targeted at car manufacturing. And the problem that they were facing was that when they made changes to their manufacturing process, their electricians had to go and rewire all of the contact and relay circuits, right, to implement new algorithms. And this was very costly and time-consuming. And the idea of using computers and software to solve problems was kind of gaining prominence. And so then people began to look into the possibility of replacing hardwired physical contacts and relays with software versions. And so the first actual practical implementation of that was in 1968. Currently, so this was as of 2023, the PLC market is about a $15 billion market, and it's projected to go up to somewhere around 24 billion by 2032. So it's rapidly growing, and the reason is primarily the push for increased automation in manufacturing and processing industries. Founded in 1906, the International Electrotechnical Commission, or IEC, is in charge of publishing various international standards for electrical, electronic, and related technologies. Their standard 61131 is the standard for PLCs. And the third part of that, which would be called IEC 61131-3, specifies PLC languages, programming languages. It defines 5 programming languages. 3 are graphical, and 2 have a textual interface. So let's list these out here. Abbreviation, full name, and the interface. So the first is LD, which is ladder diagram. And this follows essentially the ladder logic kinds of symbolism that we've been talking about previously. This is a graphical programming language, has a graphical interface. Then there's FBD for function block diagram. This is also graphical. And the third graphical language is SFC, or sequential function chart. Again, also graphical. Then there are 2 text-based languages, ST for structured text, which is derived from the Pascal programming language, and so it's basically a general-purpose text-based programming language, so textual. And then instruction list, which is also textual, which looks a lot like a microprocessor instruction set or assembly language. That is deprecated. In other words, it's discouraged. Its use has been discouraged since 2013. So there are still IL programs in use, but generally programmers are discouraged from using it for new programs. It's rather cryptic, and you can probably do the same thing much better with structured text if you want to do a textual program. Ladder diagram, as you'll see, uses essentially the ladder logic kinds of illustrations that we've already been working with. And it's very intuitive for people who have a background with contacts and relays and things of that nature, technicians and electricians. Function block diagram is somewhat reminiscent of the way we've been looking at taking logic gates and putting them together to make higher level functions, and then putting those into a chip with input and output pins, and then building up things in that manner. We can do this similar things with so-called function blocks in function block diagram. Sequential function chart is reminiscent of flowcharts. And so just like flowcharts, they're not really targeted at working on the nuts and bolts of what has to be done at every step of, say, a manufacturing process, but rather at looking at a very high level of the flow of control from one step of the process to another, with transitions targeted by changes of inputs and things like that. In that sense, there's kind of like, a little bit like the state machine idea, where the different states would be, the different steps in the process, and you would have these different input conditions causing transitions from one state to another. Structured text is a high-level block-structured language. It's derived from the Pascal programming language, which was very popular in the 70s and 80s. And as a high-level language, which has the constructs that you're probably familiar with from the C programming language, like if statements and for loops and things like that, it can be used in principle to implement any algorithm, solve any problem that you can solve on a computer. So you might think, well, why don't we just use that and stick with one language? And the answer is that in many applications, it's going to be easier to generate a solution with one of the graphical languages. And especially when you consider that you're in an industrial environment and your PLC program may need to be read by an electrician or a technician that's going to be in charge of wiring up the PLC, connecting it to the various sensors and actuators in the industrial environment, then there's a big advantage to using a graphical programming environment, because it's going to be much more readable and understandable to those people, and maybe to you too. So structured text might be overkill for many applications. On the other hand, there may be situations, especially if there's some sort of like data processing required, you may have to process on arrays or things like that, where things like ladder diagrams would be completely impractical for implementing a solution, and then you may want to use one of the higher level languages. One of the nice things about PLCs and the IEC 61131-3 standard is that we can mix and match them, essentially use whatever is most convenient for a particular step in the programming process. And if we have a particular step in that process that needs structured text, we can use it just for that, and then tie it together maybe with sequential function chart. Some of the simpler steps, maybe ladder diagram would be most appropriate, and so on. So we can make use of whatever allows us to most quickly and most intuitively, most understandably get the job done. So now let's think about PLC architecture. So we always need a power supply. And then our central processing unit, where the actual calculations are done. Those are essential. And then we need interfaces with the external world. So usually we will have digital inputs and digital outputs, right? These are 0, 1 variables, binary variables, which can detect if something is on or off and set something on or off. But sometimes we also want to have analog inputs. So quasi-continuous values like, say, temperature, force, or something like that, and analog outputs, especially for things like controlling a system with feedback, like a robotic system or a robot arm, something like that. Okay, so those will be some basic modules. And many, especially high-end PLCs, come in modular form like this, where you would buy these different modules separately and you'd stick them into a rack and then wire them up one to another. Now, for smaller types of jobs, you may have a few of these that are integrated into just one block. It makes it simpler and cuts down on the cost. So, for example, here we have PLCs mounted on a rack. There's a power supply over on the left here. And then your CPUs are here in this block. And then you have various input and output sections that can be mounted. And the nice thing about this modular structure is that if you need more inputs or outputs, you can just put more of these I/O blocks on there. And whatever blocks you need, you put on and wire them up to external devices, and then they're connected to the CPU, and it can read these various values, make calculations, and then set or unset various digital outputs or set the different analog output levels, and so on. Now, different manufacturers may have different conventions, but generally, for your digital inputs, you'll have designations such as maybe like %IX 0.1 for one of those input variables, and you can then associate that with a text variable name in the program. So the IX indicates a digital input. The 0 would be the 0 circuit block, and you could have multiple of those, so IX1, IX2, etc. And the 0.1 means the first input in that block. Okay, so you can just add as many blocks as you need. So this could go 1, 2, and etc. And this could go 0.2, 3, and so on. So you just add as many blocks as you need. For the output, we would usually have a designation of something like %QX, say 1.2. And again, this is the block, and this is the particular input in that block. Likewise here, this would be the block module, and this would be the particular output. Okay, so this would be for digital input, and here for digital output. Okay, so different manufacturers may have variations on this, but you'll see something like this. For analog signals, we need a standard for, say, voltages and or currents. Pretty common standard voltage range would be 0 to 10 volts, although you could have a shifting of that, but that's fairly common. So inputs from 0 to 10 volts, or if there were currents, pretty commonly you'd have 4 to 20 milliamps. That's kind of interesting that the lowest isn't 0 there, and one of the reasons for that, then this becomes useful if you want to be able to detect if one of the wires coming from your sensor, say, is broken. Because if it's broken, you get 0 milliamps, so that would not tell you that it was a low-level logic, but rather that the wire was broken. Okay. So you can use either voltage or current, and these are standard ranges for that. For input, in that case, you might have something like this, %IW, maybe 0.1, okay, for analog input. And %QW, whatever, 1.2 for your output. That's your analog output. All right, so those would be the most common types of modules that would be added together to make a PLC system. If you had, let's say, your 0 to 10 volt input here, now they're not actually stored as true continuous variables, right? They have to be stored in a digital system, and so they're stored by performing an analog to digital conversion with some number n bits. And very commonly, you'd use n equals 16 bits, and then you would have 2 to the 16, which is 65,536 different levels that you could represent. So if you're using 0 to 10 volts, you divide it by 2 to the 16, you would get your delta voltage would be about 150 microvolts would be your resolution in voltage. Now, one of the interesting things about PLCs is that they have various tasks that they run. So here would be kind of the flow, program flow here. You would turn on the power, and when you do that, the PLC runs a program called init, or the init task. And it does that once at the start of the program. And then it goes into a loop. And at first, it runs what's called the slow task. After that, it runs the fast task. And there are repetition times associated with the slow and the fast tasks. So suppose the slow task repetition time is 100 milliseconds or a tenth of a second, and the fast task is 10 milliseconds or 100 times per second. So then we could, after we do the fast task, we could then ask, has 100 milliseconds elapsed? And if it has, then we would go and run the slow task, and after that, go back to the fast task. If it hasn't, then we would go back and repeat the fast task like this. So this would be if no is the answer and yes is the answer. Okay, so power comes on. We run the init task once and for all. That can set up variables and do things that we only need to do once. And then as long as the PLC is powered on, it goes through this loop between slow and fast tasks. First does the slow task, then goes into a fast task loop and keeps doing that until it's time to do the slow task again. Right? So this is useful because we can use the fast task to focus on things that have to be done quickly in real time, right? Reading sensors and setting outputs and things. And the slow task maybe could be used for supervisory procedures that don't need to be done that often. Okay, so it just allows us to make more efficient use of our resources. And usually, at least the fast task repetition time can be set in the program. So in this course, we'll put essentially all of our programming into the fast task, other than some initialization steps we need to do. Now, there might be, in some PLC implementations, there might be other tasks. There might be like a background task or something that's even slower than the slow task or what have you. But these are the basic ones that you'll see. Now, there are many companies that manufacture PLCs. So when we talk about PLC platforms, there's a long list of companies that we could discuss. But the two major players are Rockwell Automation / Allen Bradley, two companies that merged. Allen Bradley, especially in the U.S., they're a dominant player, and worldwide, Siemens Corporation. So these are really dominant players in the PLC market. Now, one drawback of using PLCs from these manufacturers are that the PLCs can be rather expensive, and especially you have to use their proprietary software to program them. And those software packages can be quite expensive. In some cases, you may be facing $1,000 per year per license fees. And so, on the other hand, these are industry standards, and they add a lot of bells and whistles and things that are very useful for industrial users, a lot of optimization features and things like that. So that price is not a big deal for an industrial application where you're making a lot of money, but for educational users and personal users, that's a real showstopper. So instead, we're going to work with a simple PLC that can use freely available software, okay, and also has a relatively modest cost. And this will be just fine for what we're going to do in this course, which is an introductory course, where we're not going to need a really powerful PLC, and we're not going to need a lot of optimization and checking, debugging features and things that you would get in some of these large commercial platforms. We are going to use the Finder Opta PLC shown here. It is a small yet reasonably powerful PLC package that has 8 inputs, and they can be configured to be either digital or analog. And for analog purposes, that would be a 0 to 10 volt levels. And for digital, it's just basically anything below about 5 volts or above 5 volts would be low and high logic levels. And this has integrated within it 4 relays, and those relays can handle 250 volts 10 amp AC loads or 24 volt 4 amp DC loads, and which is plenty for us. So you don't need a separate relay module or digital input and output modules, etc. Everything's integrated into one little package, and that makes it simpler to use, less expensive, and so very suitable for our purposes as an introductory course. It has a full programming environment, which is provided by Arduino, which is free to use and is fully IEC 61131-3 compliant. So all of the programming skills you'll learn on the Finder Opta can be transferred over to any other more commercial type of PLC system. Sometimes people will call a small package like this, which has integrated inputs and relay outputs, a programmable logic relay, PLR, but we'll just call it a PLC because as far as programming is concerned, it's identical to any PLC. For simulation, we're going to use the freely available program Logic Lab. It has a virtual PLC called VPLC1 built into it. This is the interface. It represents the digital inputs, digital outputs, analog inputs, and analog outputs for this virtual PLC. A nice thing about it, it has virtually the identical interface as the Arduino PLC programming environment. And therefore, we can use this on our individual PCs and simulate the PLC operation, and then that exact same program can then just be run on the Arduino. Okay, so here we are in Logic Lab, and we're going to create a new project. I'm going to put it in some directory. I'm going to give it the name of, this is going to be an XOR project. We're using ladder diagrams, so I'll call it XOR -LD, and we want to make sure from this drop-down menu we're using the virtual PLC 1 here. And you can click or not click on this as you desire. That it makes variables case sensitive or not. I just will leave that at the default. Okay. And now here is our environment. So we first have to define our variables. Go over to the Resources tab. And here's Local I/O Mapping. Click on that. And this shows for our virtual PLC the 16 digital inputs and 16 digital outputs. And then there are some analog inputs and outputs. Okay, so we're going to have two inputs, A and B. So just put the names here, A and B. Oops, A and B. And then go down to the digital outputs. And the first one will be Y. And those are our three variables that would interface with the real world in an actual project. Okay, so now we come over here and we want to go back to our project. And here's the name of our project. Click on that and then right click, and it says add new program. So we're going to do a ladder diagram, so make sure that's clicked. Give it a name, say just LD1, and we assign it to one of the tasks. We'll use the fast task and hit OK. So here is a template for a ladder diagram program. Right? So you just have this rung, and here's a contact, and there's a coil. Okay, so let's go ahead and you can either double click on this coil here and it'll bring up this little window, or you can right click and say properties and you'll get the same thing. So give it the name. This is the output is Y. This is going to be a normal coil. It could be a negated coil, meaning that the logic would be the inverse, but we're not going to do that. And then these other set and reset and other things, we'll talk about those later. Okay, hit OK. So there you go. There's our output coil, variable Y. And now we want to get the XOR logic function. Now, if we just wanted a simple switch where Y was equal to A, we could just go in here for this contact, go to Properties, give it the name A, and that would then just be the function, logic function that Y is equal to A. But we want to implement the XOR function. And so we need two parallel rungs. So go here, select this contact, right click, and say new parallel contact. So that makes a new contact in parallel. And in our diagram, that's going to be not A. So right click and say properties, give it the name A, but then say negate. That makes it not A. And there you see the negation normally closed symbol. Now we also want to have then, right, this would be, of course, A or not A, which would always be true. But what we want is A and not B. So we need to add another contact right after A. So click on A, right click, new contact. That'll put a new contact right after that. And that's supposed to be not B. So right click, properties. We want to negate it. Give it the name B. So there's A and not B, or not A and B. So on the not A, right click, properties. Oops, sorry. Right click, not properties yet, new contact. And then right click that, properties, B, and it's normal. Okay, so there is A and not B, or not A and B. That's the XOR function. So we are now done with our ladder diagram program. Now, this is a relatively simple program. We could continue to have more rungs and things in here in this network, or we could go and add a new network down here with some other variables and things, and then these could all interact. So let's delete that. We don't need it. Okay, so now at this point, we're ready to compile this and run it. So we're going to be doing this in simulation. So we go up to debug and go into simulation mode. And look down here on the lower right, you'll see connected. Okay, so everything's working properly. This is the VPLC1 interface. Now, then we go up here and we go to project, and we want to compile, or we can just hit F7. It'll compile it down here in the output window. No warnings, no errors. Okay, so everything's good. And then for online, we want to come down here, download code. Now, with a real PLC, this would actually physically download the code that we've compiled into the PLC. But we're simulating that. So we hit this, download code, or just press F5. And it might say this, cold restart required, whatever. Just go ahead and say yes, that's fine. All right, so down here you see source OK, connected. And here's some icons here. This is an icon that'll bring up that window, which allows you to toggle the VPLC interface. This shows you the different variables. Often we'll just keep that off. And this will turn this to stop, and the green check mark will cause it to run. Okay, so this should be the XOR function. Let's see. Here are the two inputs. This is A, which was the digital input 0, and B, which was digital input 1. And then this digital output 0 should be the Y. So if A and B are both 0, the XOR function is 0. If A is 1, yeah, the XOR is 1. Okay. If B is 1, the XOR is 1. If they're both 1, it's 0. Right? Exclusive OR. Okay. So indeed, we have now implemented the exclusive OR function. So that's an example of a ladder diagram program. Now let's see how to do this XOR logic function in function block diagram. So we'll go File, New Project, and I'm going to call this XOR-function block diagram. As before, we go over to our resources. We have to do our local I/O mapping for our variables. Variables A and B will be our inputs, and variable Y our single output. Go back to project. And now we will say add new program. We want to be function block, a diagram type of program. And I'll just call this FBD1. Assign it to the fast task. There we go. So we get this workspace here, right? This is a network area. And we can make new networks if we want to. It does not have a rung in it because we're not in ladder diagram. Now, I find it useful to go up here and say View Toolbars, Function Block Diagram Bar. And that brings up these little icons here. You can do the same thing with a right click and new objects, etc. But this is just convenient for me. Now, let's put our two input variables in. This is the variable icon. So we'll click there. And we're going to have A as one of our variables and do the same thing for B. And we can put it anywhere we want. Once we have these, we can move them around. And our output is going to be Y. And I would like my output to point in the opposite direction. So right click, switch direction. Right. So we're going to have A and B are going to feed into some function block, and then Y will be the output. Okay. So up here, this is your new block. So click on that. It brings up this window, and here are the different things you can select from. We want operators here, and I'll unclick function blocks. So here's things like, or and equal and etc. And down at the very end is XOR. Okay, so click that, say OK, and then click this mouse cursor anywhere, and there's an XOR gate. And then we can move these around as we wish. Something like this, say. And now we need to wire it up, and that is this icon up here. That's the connection icon. Click on that, and then you can left click on any two of these terminals and wire them up. So click, release, move to the next terminal, and left click and release. And do the same thing for Y. So there now we have wired up. Y is XOR of A and B. So from this point, everything goes the same as it did for the ladder diagram. Now, it's always a good idea to periodically save your program. We want to go into simulation mode, debug simulation mode. We want to go into our project and compile. Look down here, no warnings, no errors. We want to go online, download code. And now we can come and open up here and look at these different windows. And let's see, yes, there is the XOR function. Okay, so that's how to do the XOR function in function block diagram. Now let's look at structured text. New project. I'll call this XOR-ST for structured text. Again, make sure you're using the virtual PLC. As always, go into Resources, Local I/O Mapping, and set up your input and output variables. As we'll see later, you can have internal variables, right? You aren't limited to just the input and output variables. But for most simple programs, you just make use of the input and output variables. We'll see how to define internal variables later. Great, then go back to project, click on the name of the project, right-click, add new program. We want structured text. So let's call this ST1, assign it to the fast task. And now we get a little programming environment here, and this will be numbered lines. So first line is 1. And here's what we do. We say y, and the assignment operator is :equals, whereas the equal operator is a test for equality. So y : equals A XOR B semicolon. And you can see if you do more lines there, in this case would just be blank lines. So that's our program. All right, let's save everything and go online. Debug simulation mode, and then project F7, no warnings, then online, download code. Here is our virtual PLC, and let's see. Yes, one of them, the A variable's on or the B variable's on, but if they're both on or both off, no, we don't get anything. So it is the XOR operation, like it says right there. So that's how to do that same process using structured text. Okay, so we've seen how to write a very simple program in 3 of the 4 non-deprecated PLC languages. Sequential function chart is too high level for a simple program, generally speaking. And as we'll see later, it's kind of like you may have been exposed to flowcharts. And so SFC is kind of like a flowchart programming language. And it's useful for taking different operations, which individually might be programmed in ladder diagram or one of the other programming kinds of environments, and putting them together and giving you a high-level view of the flow, say, of different manufacturing sequence operations and things like that. So not really made for doing nuts and bolts types of programming operations. So from what we've seen, it might appear that structured text should be the default. After all, we just saw one line of structured text to get the XOR operation, but it has, for loops and while loops and all the kinds of things that a normal programming function has. It's actually based on the Pascal programming language. So why not just use a general purpose programming language and you can implement anything? But in fact, LD is the default. And when you talk to PLC programmers, they'll tell you they do the vast majority of their programming in ladder diagram, although not pure ladder diagram, not just contacts and coils and connections and things, but also this will be ladder diagram plus some function blocks. As we'll see, in principle, you can implement any state machine in pure ladder diagram. And since any computation can be represented as a state machine, the output of any programming language can be represented as a state machine, you could, in principle, program anything using pure ladder diagram. But there are some operations like timers and counters and things like that that are so clunky and ponderous to do with pure ladder diagram that instead, to make things more efficient, we add in function blocks. So we'll talk about that later on. Still, even for something like this XOR operation, ladder diagram is the default. And the reason is because programmers are not just programming for themselves, but they're programming so that electricians and technicians can actually connect the PLC to an industrial process and maintain it and operate it. And electricians and technicians are much more familiar with electrical circuit diagrams with contacts and coils like you have in ladder diagram. So it's much more intuitive for them. And if you just give them some lines of program code, they're going to be kind of at a loss of what it even means. If I can have a diagram, right, like we just saw, that does something, looks like this. Now this, of course, is actually originally developed from wiring diagrams for relays and coils, and uses the idea of normally open and normally closed relays or contacts and coils. And so electricians and technicians are already familiar with these kinds of ideas. And this idea of having, contacts in series, they wouldn't call that the AND operation, but they would understand that this implements something that current has to go through this contact and through this contact. Or if you have things in parallel, they would understand that current can go through either this path or this path, right? So they have an intuitive understanding of the AND and OR operations, but they haven't formally studied, logic systems and logic circuits. So this is a very good balance between basically having the flexibility to implement arbitrary logic functions and to have a format which is understandable to the people that actually have to use and interface with it. And that's why, many programmers that program PLCs will tell you that 90% or more of their programming is done in ladder diagram. So we will focus primarily on ladder diagram, but we will do some programming with function block diagram, a little bit with structured text, and we'll see a little bit of how to use sequential function chart to make a high-level representation of a very complicated industrial process.